Hi everyone and welcome back to your channel Fundamentals of Engineering with Farhad. Mechanics of Materials, Maximum Deflection Calculation in Beams. So if we have two simple support beam, we want to calculate delta maximum at its center. We have different approach to calculate it. Last time we solved this problem with the help of integration from the load function, and this time we are focusing on solution 2, which is determination of elastic curve from moment. It's a bit easier approach, and in the next videos we talk about the solution 3 and 4, which are moment area method and combined method. Solution 2 is a bit easier than the first solution because it just starts at the middle of the solution 1, kind of. So again, based off mass and also concept, we have the area under load is shear, area under shear is moment, area under moment is angle of rotation, and also the last integration, which leads us to deflection from load. Last time we started from load, integrate the load function, integrate shear, integrate moment, integrate theta to finally get delta or deflection. But this time we start from the halfway through. So in the second solution, which we are working around in this problem, we start from the middle of the problem. It says so we don't need to worry about the top part, and we just ran to develop the moment function and use two integration to get the theta is the integration of m dx and delta is integration of theta dx. So we just work around in on two of the integration, but we need to cut the beam through and get the moment at the distance of x. So we need to cut the beam through and get the moment somewhere at a distance of x from, for example, support A. So if we do so, RA is just replaced from the top, so half of the load goes to A, the other half to B. So RA is simply WL over 2, and there is a moment, internal moment in beam. We call that M sub X, and the when you convert the distributed load to a concentrated load, it just turns to be Wx and applies at x over 2 from either each side of the R beam. So summation of mx goes 0, including mx, it just says mx plus wx squared over 2 minus reaction times x in counterclockwise, that's a negative WLx over 2, and it just gives us the moment function. The only difference, the only starting steps for this method is you have to cut the beam through and jot down the moment equation and avoid two steps from load to moment. So that's how we start somehow from the middle. So then d squared y over dx squared is m over ei. We already calculate our moment function. So, and that's definitely times 1 over ei because which comes here. And then by integrating moment function, we reach to, by integrating moment function, or area under moment is our shear diagram or theta. My bad, the theta, the angle of rotation. So if you integrate the top equation, it just gives you wx squared over 2 negative, it just comes to 1 over 6 wx cubed. The other part is 1/4 a quarter of WLX squared plus a constant which creates during the first integration. Then from theta, again, we integrate theta to get delta. So integration of theta gives us the delta function, and definitely the other constant added to our problem. So this is C2 and this is C1 due to 2 times integration, each times a constant added to our equation. So we have the function of y, and now let's jump to boundary conditions. And as soon as we have like our equation for delta, and then makes a boundary condition at x equal to 0, y is 0. So at x equal to 0, y is 0. It just gives us c2 is equal to 0 as soon as we do know c2. And by that, we need to replace 0 in this term. All this goes 0. Y is 0 at x is equal to 0. Then c2 is 0. And then by the second boundary condition at x equal to L, again y is 0 because there is a reaction here. It doesn't let any upward and downward movement, so it just gives us c1 is equal to a negative 1 over 24 WL cubed. As soon as we have that one, we can jot that down and rearrange the y equation based off c1 and top equation. So it just gives us this term after simplification. And as soon as we have our W function, we can easily jump down. We do know that the maximum deflection occurs at the center due to the symmetry. So Y max is at x equal to L over 2. And by replacing L over 2 instead of x, we reach to delta maximum or Y max, which is 5WL to the fourth over 384 EI. There is a clockwise and counterclockwise theta at A and B. In terms of their parametric or numeric value, they're identical due to the symmetry, and theta at A is simply comes from the theta equation when you replace x by 0, and it just gives us theta A is equal to theta B is WL cubed times over 24 EI. We get the same result for theta and also delta in previous calculation. The only difference in solution 2, we calculate delta function or y based off moment. My bad, not load this time, from moment. And this is exactly identical to the answers, the same answers when we had it from a integration for consecutive integration from load to delta. Thank you. In next video, we'll solve it with much easier approach, which is our solution 3, and that's moment area theorem.